Okay, let's get started. We are very happy to have Niazadeh from Cornell. Rad has done a lot of interesting work in algorithm mechanism design and theoretical online machine learning. And he will soon be a postdoc at Stanford. And today he's going to talk about Bernoulli factories and black box reductions.
Thanks, Balu. Thanks, everyone, for coming to my talk. So I'm going to talk about black box reductions in mechanism design. I didn't put the word mechanism design in the title because it was very ugly after I put it there. So just black box reductions in mechanism design. So this is the type of talk that I'm talking about algorithms on one side and mechanisms on the other side. So we always have this question that we are designing algorithms for non-strategic people or basically no people at all, which is the algorithm design question. And then we have the algorithm design question for strategic human entities, which is the mechanism design question. And I'm trying to look at the computational complexity question of the mechanism design through the lens of designing polynomial time Turing reductions or Cook reductions. And the problem I'm looking at is maximizing social welfare. So I'm going to define what maximizing social welfare means, and I'm going to define the type of reductions I'm interested in. So just stay with me. So as a running example in this talk, I'm looking at something that I call it the lift problem, but nothing special about this problem is important. I'm just trying to make the techniques understandable through this problem. We can replace this problem with anything. Just don't replace it with maybe Uber problems. Lift problems, okay. So what is lift problem? So in the lift problem, in every second, we have passengers that they want to commute from their location to some destinations. And then we have drivers that they want to pick up the passengers and give them rides to their destinations. And we assume that each passenger has a value for the ride that he's interested in, and giving the ride has some cost for the drivers. Okay. Now the goal of the lift, if Lyft is a good company, is maximizing social welfare, which in this example is defined to be the total generated value. Drivers have negative value, so I call it cost. So the social welfare is basically total generated value minus total generated cost. And here, the important part is, for the drivers and the passengers, their value for the ride and maybe other parameters that is important for the mechanism design is considered to be private information, things that they know but no one else knows. And therefore, they cannot strategize. And that's what makes this problem hard. Now let's remove the strategic component from this problem, and we get to another problem which I call it the UPS problem. So what is UPS problem? In the UPS problem, every morning, UPS stores, they have packages that needs to be delivered to the UPS dispatching center. And then we have UPS trucks that they want to go to these UPS stores, get the packages and deliver them to the dispatching centers. And then serving at a store has some value for UPS and has some cost for the UPS due to the cost of the truck going from one location to another, maybe the salary of the truck driver or the fuel consumption, or etc. And now the goal of the UPS as a company is to maximize the total benefit, which in this case, let's say it's like the total value minus the total cost of UPS. Okay, so this is a non-strategic problem. And if you look at the special case that, for example, there is just one truck and it wants to serve the UPS store, and let's imagine that the truck can just load one package, then this is basically the traveling salesman problem, if you think about it for a second. So we know this is like a computationally hard problem. There are approximation algorithms, or maybe in practice people are running heuristic algorithms for this problem, but this is hard, even without considering the incentives. And the original non-incentive problem is also hard, right? So then we start thinking, what should we do about the lift problem that has the element of incentives? Okay, let's get back to the lift example to see what are we exactly doing here. So let's say the goal of the designer is to pick an outcome. And what they define the outcome space is basically who picks who. Which drivers are going to pick up which passengers and at what time. This is a very large set of possible outcomes. And the mechanism designer is picking one outcome and charging each person with some monetary payment. Basically charging the passengers with positive monetary payments and charging the drivers with negative monetary payment, which means gives them some money. So the designer, the mechanism designer, is picking an outcome payment. And the question is which outcome to pick and what payments to charge, so that we have a mechanism that at the end, when everyone is acting strategically, we maximize the social welfare. Okay? So we are looking at incentive compatible mechanisms, which is the case that no player is better off by a strategist. So you assign the outcome payments in a way that no player deviates or makes sense for any player to deviate. And now we try to maximize the social welfare, which is the total generated value. Now the question is how to design such mechanisms, okay? So the first approach is looking at this problem with the incentive constraints as an optimization problem. A new optimization problem that now has incentive constraints as a condition, as constraints. Basically, you have one constraint for each buyer that says this player doesn't better off by misreporting, but the problem is now you will, if you add that to the non-strategic problem, you will have an optimization problem that has maybe uncountably many constraints, because you need to look at any deviation, and maybe the strategy space is continuous. Therefore, you have like uncountably many constraints. So the problem is you need to design a new set of machineries to attack this new problem. And this is why mechanism design is a hard question. And this is what traditionally people in mechanism design are doing. They're not trying to basically solve the non-strategic problem and then add incentive constraints. They're looking at this problem as a whole, and then they try to come up with ways of attacking this problem.
So here you focus on social welfare because
Yes.
the problem is going to be simpler, or could you I know that you haven't talked about your method yet, but could your result?
It is a completely different problem if you look at other economic research.
Because for the leaf, probably the better objective would be
like revenue, right? Yes. So I'm going to talk about that if I have time for a minute. Actually, we have a follow-up work which looks at other objectives. There is also this line of work by Daskalakis, Yang Tsai, and Matt Weinberg that they have basically looked at Blackbox reduction from revenue maximization to welfare maximization for just optimal revenue. Yeah, so it's a different story.
So what's the difference? What's the difference with this other work?
So they're looking at the reduction from optimal revenue maximization to welfare maximization, or let's say virtual welfare maximization. So the question they are solving is basically if you can find the virtual welfare maximizers, then you can actually.
But I thought it was for any objective, no?
So they have this other thing that so you can ask the same question for welfare too, right?
Yeah, yeah.
So it's like so you have an algorithm that can solve the virtual welfare optimization problem, and that gives you a mechanism for optimal welfare.
Okay.
Right? But still the optimal is the important part. So you do a reduction from optimal mechanism design to optimal algorithm design. Maybe, and by the way, for the welfare, it is a stupid reduction because VCG does the job for you. Mm-hmm. And you don't even need to do the entire virtual welfare. Even for the objective of welfare, if you do what Matt and Yang were doing, you need to have access to a black box that solves the virtual welfare problem. But still, there is a reduction between optimal to optimal. And this is exactly what I'm avoiding here. Because for the objective of welfare, if you want to do a reduction from optimal to optimal, this is exactly what VCG does. You solve the optimization problem for the welfare maximization, there is a pricing rule that will make it truthful, right?
But I think the other reduction is approximation preserving too. So if you have an approximation
that is true for some particular objectives, and still you need to have like a guarantee that your algorithm is alpha approximation.
Sure.
Right? Sure. But if it's like a crappy algorithm, you cannot match that algorithm. These are exactly the type of things that I'm avoiding. Mm-hmm. So I want to look at like a general reduction. We'll get to that point, but that was a good question. So here's the second approach. The second approach is the following. So I actually look at the welfare maximization without incentives, the UPS problem in this example. And then one way is what Bernoulli said, like finding the optimal solution, and then using that, which is still a hard problem, but suppose you have access to a black box that can find the optimal solution, and now you want to create a mechanism. But another thing is maybe you have approximation algorithms, or even you don't have an approximation algorithm, you actually have just some heuristic algorithm that, for example, you know it works well in practice, but there is no guarantee. It might be a crappy algorithm in general for worst case instances, but like for the randomized instances that you observe in practice is actually a good one. Now the question is the following. Oh, actually, let's get back to the point that I explained earlier. If you have access to the optimal solution, this reduction is very easy. This is the well-known solution of economists, Vickers, Clark, and Groves, called VCG mechanism. So what VCG says is the following. So if you can solve the optimization problem without incentives and have like a black box, let's say n is the number of buyers or number of people in this system, then with n plus 1 calls to the oracle, you can actually find a set of pricings that together with that allocation rule will give you a mechanism that is truthful and achieves the optimal welfare. This is called VCG mechanism. I'm pretty sure everyone is familiar with. So it's like a universal way of transforming any optimal solution to the optimization problem to a mechanism. Now here's the question I'm asking, which is exactly what Manouris and I discussed. Is there a universal way of transforming any algorithm into a mechanism so that I preserve the social welfare? And the setting I'm looking at is any complex environment, but I can say, maybe it's a better term, the VCG environment. You know, when people think about VCG is like, it's voiced for the most general case for mechanism design, and that's exactly the type of setting I'm looking at.
So what does transform here really means? It means that if I run the original heuristic algorithm, whatever it outputs, you can get the same exact output here.
So I just use the heuristic algorithm as a black box, and I may actually manipulate with the allocation rule.
So then why not running a good approximation algorithm? If you have a heuristic, instead of run a good approximation algorithm, say that this approximation is better.
Maybe that doesn't exist for the problem you're looking at. Right.
Okay.
But yeah, I mean, that's a very good question.
Would it be like better to use the algorithm which gives you some
It depends how you define better. Let's go to the extreme points. Suppose your optimization problem is not hard, and VCG can be done in polynomial time. Then rather than doing whatever I'm saying today, just run VCG. It's a polynomial time algorithm, it's a polynomial time mechanism, and everything is good. The problem is maybe VCG cannot be done in polynomial time. And again, for approximations, maybe approximations cannot be done.
Yeah, but then heuristic also, if you change your input in a very pathological way and end up with something, then you cannot say the heuristic was good.
But you see, like, this is very problem specific, right?
Okay.
I don't want to like go into there are many papers on this topic. They looked at like a class of algorithms that work, and they try to find like what kind of a structures algorithm need in order to make the reduction possible, you know, alongside what you're thinking. But now I'm looking at like the most general setting. There is no constraint on algorithm. You just give me some algorithm, it's a black box. I submit the values, get some allocation. That's exactly what.
But then what is the guarantee? I guess you're going to say.
Additive epsilon in welfare, but I get to that. Okay, so good. I think now is the right moment to formalize the black box reduction problem. So let me actually define the multi-parameter setting or the VCG setting again. So here is the abstract setting I'm looking at. I have n users, n agents, n readers, whatever you want to call them, and each one has a private type denoted by TI. And I'm looking at the Bayesian setting, which is very important here. I'm going to explain why. Which is the setting that you can assume there are underlying common prior distributions for the type of agent I is sampled from Fi, independent from other agents. And we have a set of outcomes. I call it outcome space. And then for each outcome, depending on agent's type, it gets some value. So this value function is a fixed function, val. And you just plug a type and an outcome, and you get some number. Okay?
You're assuming Fi is known.
Fi's are known by the auctioneer. This is like a Bayesian assumption, right? Now, a mechanism is basically the following. I'm looking at direct revelation mechanisms. There is a revelation principle that shows this is enough. So if you don't know what the revelation principle is, just believe me, this is like the most general setting you can think of. Bidders are submitting their types. It might be a non-truthful submission, but they just submit some numbers. We want to be in, and they're not numbers. They're like elements of type spaces, and type spaces are general cells. So they submit P1 through Pn. And then the mechanism designer that has two functions, the allocation and payment, picks the outcome A hat of B and charges each person with some payment Pi. So what is the black box reduction? And the utility of the user is value minus payment, the quasi-linear assumption. Now, what is the black box reduction problem? It's the following problem. So I have users, they have types, they submit their type. Oh, and I have access to black box allocation algorithm A. So what is my allocation algorithm? What is my black box? So the input of the black box is a profile of types. Let's say S1 through Sn. So basically, you create a profile of types, you give it to the algorithm, and the algorithm spits out some outcome. It's the way that you can think of any algorithm, right? And I assume that my mechanism has access to this allocation algorithm, can send as many queries as wants to this allocation. Now players submitting their bits, the mechanism interacts with the black box allocation algorithm, now picks an outcome and charges each person with some money. And the promise it has is the following kind of incentive compatibility, which is called BIC, or Bayesian incentive compatibility, which is the case that no player is better off by misreporting if you assume that the other people are truthful and their reports are coming from their type distribution. So this is a very important type of solution concept. And the other one, which is the dominant strategy incentive compatibility, is not the one that works here. So if you have any questions about it, I would be happy to answer. So this is the way you can think of the BIC. You are an agent, and you have no idea what's happening in the Bayesian world. So you assume that everyone else is truthful, and their reported type is coming from their distribution. Now, playing truthfully is your best strategy in this scenario. Outcome and payments are picked such that playing truthfully is the best strategy for you. This is called BIC. And we are looking at the expected welfare, which is the total expected generated value by the mechanism. And the expectation is over the randomness in the types. Okay? So we are looking at efficient reductions in this computational model that you have access to a black box, meaning that we need a black box access to some algorithm that, as I said, can be like any approximation algorithm or any heuristic. And now we need a mechanism that has these three properties. First of all, it is BIC. Second, it has negligible welfare loss, meaning that the expected welfare that your mechanism gets is no less than the expected welfare of the algorithm by a factor of epsilon, by an additive factor of epsilon. So you're not going to lose more than epsilon amounts in the welfare. And then the reduction in this computational model is completely polynomial, meaning that the number of queries you make to the allocation algorithm plus any extra computation you need is polynomial time as a function of n and 1 over epsilon. Okay, so this was open. Optimal algorithms are easy, by the way, as I said. So if you think about non-optimal arbitrary algorithms, and your solution concept is something which is a stronger solution concept than BIC, DSIC, there is no hope. This is like hopeless. You cannot get a transformation from algorithm to a mechanism for the dominant strategy incentive compatibility, which is the case that no player is bettering off by misreporting no matter what the other people reported. But if you are,
that cannot, information theoretic cannot, NP completeness reduction cannot, or some other
yes,
cannot.
that's an information theoretic cannot.
Okay.
Good question. Now, well, okay, so here's the caveat. So you can always do VCG, right? So that means if you're allowed to do VCG, the information theoretic lower bound even doesn't make sense, right? So in that sense, it is a complexity lower bound. Because you can always do VCG. Forget about what allocation algorithm I give to you. And VCG is a dominant strategy incentive compatible mechanism.
So conditional on the algorithm, it's information theoretic.
Yeah,
Okay,
conditional on the algorithm is information theoretic. But if you don't assume that, and you're allowed to do non-polynomial time, basically, if you calculate the sample complexity, it is information theoretic. But if you calculate the total computation, it is a computation complexity lower bound.
Which score? Is this a lower bound based on some work by Bernoulli and Nicole,
Yes.
etc.? This one? Okay.
Good. So people have thought about BIC, and then there is this line of work that started by the work of Hartman and Lucier, and concurrently with Huang and Bei, 2011, that they solved the problem for single dimension. They showed there is a reduction for single dimensional from mechanism design to algorithm design. And then the progress continued 2011 for the very general multi-parameter setting, the one that I talked about. Just add this assumption that the type spaces are discrete. We can solve the problem. We get a reduction. This is this work by Jason Hofstein, Bobby Kleinberg, and Azarash Malikian in 2011. And then people started thinking about the general type space, basically why we need to think about discrete. And then there was no progress. There was no, so people talked about like multi-parameter good algorithms, like multi-parameter packing problems, which are another type of good algorithms. And they had results, but the problem was open. So here's what we show. We show that there exists a BIC mechanism that exactly gets the promise that we wanted. You don't lose more than epsilon in the expected welfare, and the Ryan term is polynomial in n number of bidders and 1 over epsilon. And that's for the multi-parameter general type spaces.
So the welfare of A side of it, that's the heuristic black box. Which A is the one that you need to measure welfare on in that? Is it any A? Is it the one of the many that you query, or is it for the particular?
No. So this is expectation over. So if by query you mean so a query is a type profile, right? Mm-hmm. So this is like expectation when the type profile is drawn from the type distribution. Remember, it's a Bayesian board, right? Type of the bidders are drawn from known distributions. Now we can measure a black box allocation algorithm by just drawing types from that distribution and then taking expectation. Measuring the welfare and then taking expectation. It's called expected welfare. Like you measure.
Okay, so it's not so it's certainly the case that you could have a very easy instance and do a bad job on it.
And by instance, you mean type profile.
Type profile, yeah.
Yes, that's true. That is basically the promise of the DSIC. This is why the DSIC type of reductions are not possible, but BICs are possible. Because you relax your welfare guarantee from, I mean, it has two parts, right? So one is that you relax the welfare guarantee rather than being 0.5 epsilon far, by being epsilon far in expectation, and also you relax the incentive constraints, like an optimization problem, right? So you relax both the guarantee in the objective function and also in the constraints. The BIC constraints are weaker than the DSIC constraints because they are basically the in expectation version of the DSIC constraint. Good questions.
But it might be not a good question, but is it clear that welfare of A tilde is smaller than welfare of A, or that may not happen?
No, it's not clear, actually. Okay. You may, yeah.
You may get something which is suddenly way better. Yeah.
Yes. I have thought about that, actually, but I don't have a clear answer that whether. Let's say it in this way. I don't have a proof for upper bound. I don't have an example that shows that you can always get a smaller. I mean, you always get a smaller than. I mean, I don't have a proof that shows you get always a smaller. And I don't have an instance that for which you get more. So
if A is an algorithm that finds the minimum welfare solution,
then you're saying that anything is going to be better.
So you have a proof that something, yeah.
No, but it's strictly better, right?
Okay.
So you have to find an example that has like just one minimum. You cannot find that one, and you should be able to find that one minimum in polynomial time, because this is like a polynomial time algorithm. Yeah. I don't say even this is like an interesting problem to work on, but this is just the first thing comes. Good. Okay, so I'm trying to give you a sense of how does the reduction work. Here is my plan. So I show you a general, so I zoom out and I look at the reduction from above and try to show you like what does the reduction look like. And then I zoom in the next chapter on the heart of the reduction, and I will go through the proof of keys in detail completely. And then I will show you why these two together won't give you a reduction, and will give you the later part. So this is my plan of showing you, because here's the problem when you're presenting this work. This work is relying heavily on some existing work on black box reduction into mechanism design, and it's basically a reduction from it's a reduction inside a reduction.
Yeah.
And so I decided for this talk to do the following, like show you how does the reduction look like, and then zoom in on the heart of the reduction and go through the proof of that in detail, which is the interesting part, I would say. So here is my plan for doing some reduction. Let's imagine that you have a user, you focus on one user, and here's what you want to do. You want to transform this user's type to something that I call it a surrogate. So you do the following. I don't know why. Okay. So you have IID draws from the type distribution. I call them surrogates. Let's denote them by S1 through Sk. And my plan for doing the reduction is the following, which I call the surrogate mechanism. I ask the agent to report the type. Just zoom up in one agent. I ask the agent to report the type, and then I assign one of the surrogates to his type. And then, rather than using his type in the allocation algorithm, I just use this surrogate in the allocation algorithm. Okay? And I imagine the others are other surrogates are drawn from their type distribution, and I look at the outcome that this procedure gives them. And this is going to be my outcome. And then I charge him with a payment that makes that outcome truthful. I haven't yet said how to pick the payments. I haven't yet said what kind of surrogate I pick, but this is my plan. So my plan is draw IID types from the type distribution, call them surrogates, somehow assign the agent to one of these surrogates, and use that surrogate in the allocation algorithm. So then, if you zoom out, you have different people. And for each one, you run a surrogate mechanism that transforms the reported type to some surrogate. And you just plug those surrogates into the allocation algorithm for the optimization problem. Just one call. And it gives you some outcome. And you output that outcome and charge people with some prices. This is how the reduction looks like. So now let's see what type of surrogate mechanisms I need to be able to do such a reduction.
So the reason why you look at surrogates, because we know like our discrete type space how to do it. So you kind of want to just have like a discrete number of surrogates.
No, so we still have discrete number, right? Discrete infinite number of surrogates is countable. Yeah. We still have countable number of surrogates because otherwise the reduction is not going for a long time. The part that discrete matters is when you're assigning the agent to surrogates, which I'm going to go through next. But it's not like I'm creating infinitely many surrogates in this reduction. I still like draw some number of surrogates. The number is polynomial in number of bidders and 1 over epsilon. And here even bidders doesn't matter. It's just polynomial in 1 over epsilon. Okay. So what do I expect from a surrogate mechanism to be able to do anything meaningful? So the previous reduction that you saw has one property. So for example, you try to make the reduction, you try to make the surrogate mechanism truthful for one agent, and now you expect that if you make it truthful for one agent, then it's going to become truthful for everyone. Basically, this is going to give you a PIC mechanism. Suppose this is your plan. Then you need to kind of decompose the problem into agents, and for that, you need a property that I call it the type distribution preservation. So you want to transform the type of agent to some surrogate. And suppose the way that you transform the type to surrogate is such that the distribution of the surrogate that you use is going to be exactly the type distribution of the agent. Then here is my claim. So if you assign the surrogate to the agent in a truthful way, okay, then from the truthful assignment of the surrogate to the agent, you get PIC in general. So let me explain this more. So what do I mean by assigning a surrogate to agent? So I have like IID draws of the type, call them surrogates. Now let's zoom at one circuit. Let's say Sj. So the agent has some type, Sj is drawn from the same type distribution. I look at this random variable, that if the agent plays surrogate Sj while others are playing some random strategy from their type distribution, how much value the agent gets under truthful reporting. So he has type T, he's playing Sj, so how much value does he get? Okay, so I consider to be the value that the agent gets in the surrogate mechanism. And I assign a surrogate to the agent in a truthful way, meaning that I assign a surrogate and I charge him with some payment, such that the agent doesn't get any benefit by misreporting. Okay. Then, if I have the type distribution preservation, meaning that in this assignment, the surrogate you pick has exactly the same distribution as the agent type, then the problem decomposes across agents. This is basically.
And now you're worried that because so originally you pick each of SIs from F, so that part is fine, but now you're worried that because whatever algorithm you're running may correlate T and SI, such that their joint distribution is basically not a product distribution.
Good,
okay.
Good. So one problem is that means that, so I'm doing this independently for each agent. So whatever distribution I come with is a product distribution, but it may not be the original distribution. Just imagine the following mechanism. I assign the agent to the maximum surrogate, right? So this distribution is the distribution of the maximum amount IID draws from the same distribution, which is different from the original distribution, right? So that's one concern. The other concern is the welfare. Just imagine, so you're submitting this to the allocation algorithm and get some outcome. Then the expected welfare that the agent gets from T is different from the expected welfare that he gets from submitting S. But you have to pick S such that these two are close to each other.
What is the expectation over?
This is over the other players.
So
types.
T is fixed now.
T is fixed.
Okay, I see.
T is fixed now.
But T minus I is
T minus I is drawn from the other types, and you take expectation over that. So here, in terms of welfare, it is clear what is the best way. What is the best thing to do? It's like assigning to the guy that has the maximum value. This is the best thing to do. And you hope that if you assign to the guy with the maximum value, then the maximum value is close to what the agent gets in expectation.
So what is maximum over what?
Over different surrogates. Over different surrogates. So by playing each surrogate, so each surrogate imposes some distribution or outcomes. And in expectation, you get some value. Now, the best surrogate is the one that has the maximum value in expectation. So that's the best thing you can assign to the agent in terms of the welfare. You may break the truthfulness. So you have to do this kind of trade-off, like which surrogate assigned to the agent and how to make it truthful. And this is the point of, but so far, this is clear that if we assign the surrogate to the agent, charging with some payment, that the assignment, this surrogate mechanism is truthful, you get PIC as long as you have the distribution preservation.
But you pick the surrogates completely uniformly at random, independently from the
type. But that's still because we are assigning based on the type of the agent, the distribution is not necessarily.
You haven't told us the assignment.
I haven't told. It doesn't matter what assignment you do. It's not going to be taken care of. So here is another problem I'm proposing, and then I'll show you how to fix that to get the reduction. So, but still the welfare preservation is important. You want to assign. So suppose you want to do the following. Rather than even thinking about how it's going to fit into the picture, here's the question. How to match the optimal surrogate, the one that the agent gets the maximum value to this agent in a truthful way. Even that is hard. There is an obvious way of doing it, which is basically the following. I actually look at these edges, and I find the one that gets the maximum value. I assign it to the agent, charge him with 0 money. This is truthful, gets the maximum welfare. But what's the problem? The problem is calculating this expectation requires doing an exponentially large weighted sum. Because what is the support of the distribution is the other agent's type distribution, which is exponentially big. So you cannot calculate this expectation in polynomial time. And the problem gets harder when you move from the discrete type spaces to the continuous type spaces, because even this is not exponentially big. This is now uncountable support points. So the problem is how to, we cannot calculate this expectation. Otherwise, we could just like pick the best, assign to the agent, charge him with zero money. And even that wouldn't be complete for the reduction, but I can show you how to fix that and get a reduction. But the part is, we just can sample from these values, basically. The only thing that we can do is sampling from these values. And then, so another way to approach this problem is the following. So you can sample these values, right? So for example, you can take some samples from each one. Let's say you get 1/epsilon² sample from each value, and then you get concentration. But now the problem is you won't be able to match to the guy that has the maximum value. You match to a person that is almost maximum value. You are good in terms of welfare, but you cannot make that truthful. And I'm going to go through this question in the next slide, which is basically how to solve this problem. Again, I have a single agent. So this is the right time that maybe if you haven't followed the previous slide, just like stay with me for the rest, because this is just a separate mechanism design question. And I'm going to show you a complete construction. And this is basically the heart of the reduction. And then I show you how to use this heart as a building block for the rest of the reduction. So here is the problem again. I have an agent, and I have a couple of, let's say, edges. For each edge, agent gets some value. And then your objective is assigning the one that has the maximum expectation, but you are not allowed to calculate the expectation. You can just sample from these edges, and you want to do this assignment in a truthful way. Basically, coming up with a way of charging these different outcomes together with some allocation. Okay, good. So here are the notations I'm using. The agent reports some type S, and then my mechanism is picking a distribution over these surrogates, denoted by Q, and then I charge him with some payments. This is my surrogate mechanism, basically. And I'm looking at incentive compatible allocation and payments, which is the case that the agent is not bettering off by misreporting. S equal to T is the best strategy. And then I expect near optimal welfare. The expectation of the value he gets, which is the summation of Qj, Vj, should be no smaller than opt minus epsilon. Opt is the maximum of VIs. Good. So the first question that one can ask is the following. What type of allocations are truthful? This is the classic question mechanism design. So you have like a couple of outcomes. You want to like assign one of them to this guy. What kind of probability distributions are you allowed here? At least we know one category of them, which are the affine maximizers, or let's say regularized welfare maximizers. So what's a regular welfare maximizer? So a welfare maximizer is basically a Q that maximizes summation Qj, Vj. And this is going to be a points mass on the opt. But this is not the only class of allocation rules that are implementable by some payments, meaning that you can make them truthful. Basically, if you add any regularizer term as a function of distribution, there exists still a payment rule that can make this allocation algorithm truthful. And there is a result by Moshe and Bobby that shows as long as this allocation is an affine maximizer, it's like a regular welfare maximizer, there is a polynomial way of coming up with the payments. But the main question here is the following. Can you basically implement a regular welfare maximizer without calculating the expectations and by only sampling? This is the type of thing I'm looking for. Okay, so I'm okay with regular welfare maximizers and I need near optimality. So here's the problem that I have. First, I have to come up with a choice for my regularizer, for the welfare maximizer, and then I have to show you why that choice is bounded, therefore you don't get far from near optimality. And then the third step is showing how to implement that. Now, I switch to a different machinery, which is going to be the main machinery I'm using to be able to implement allocations through sampling. I call it Bernoulli factory. And I'm going to explain that, and then we'll be back to the mechanism design question again. So what is Bernoulli factory problem? Which is, in a sense, very similar to what we are trying to solve here. So the Bernoulli factory problem is the following problem. You want to generate a new random coin from some old coins that is given to you. Or in the simplest case, suppose you have access to some random coin, that has some bias P. P is unknown, but you can toss the coin as many times as you want. Basically, you can sample from the coin. Now the question is, can you simulate a new random coin that has a bias f of p for some known function f without knowing p by only sampling? This is the question that the Bernoulli factor is trying to solve. And let me give you some examples. Some monomials are easy. For example, f of p equal to p to the power 4. How do you do that? Just flip your coin 4 number of times. If all the coin flips were heads, announce the heads, otherwise announce the tail. This is easy. In general, if you look at probability generating functions, they are easy. A probability generating function is a polynomial that the ith coefficient is the probability that x, the discrete random variable over natural numbers, is equal to I. It is a polynomial of this form. Now I claim these functions are also easy to implement by using Bernoulli factory. Just draw one sample from x and flip your coin x number of times. If all the coin flips were heads, announce the head, otherwise announce the tail. Why this gives you the probability generating function? Because if you condition on x, then this is the probability that you have a head is basically p to the power x. Now the unconditional one is the expectation of this thing, which is the probability generating function. Good. Now I generalize this problem. I call it a multivariate Bernoulli factor. In the multivariate Bernoulli factor, you have a couple of coins given to you with unknown biases, but you can sample from them. And now you have a multivariate function of the samples, and you want to simulate this new coin. For example, one can think of linear multivariate Bernoulli factory. Let's say mixing two coins. You have a coin with P1 bias, another coin with P2 bias. You want to generate a new coin that has bias P1 plus P2. Suppose you know that P1 and P2 are between 0 and half, such that they sum up to something between 0 and 1. And this is also known. I'm not going to show you how, but this is a recent paper kind of by Huber that showed this can be done efficiently. These are basic building blocks that I'm going to use in my construction. And then this is the most important one. It's a combinatorial generalization of the Bernoulli factor problem. Now, rather than simulating a coin, I want to pick a random edge. So I have, let's say, 4 coins with unknown biases, and I have samples from these coins. And suppose P1 through P4, they sum up to 1. Basically, they're like a vector in simplex over the coins. Now, the question is, can you pick edge number 2 with a probability that is equal to P2? Basically, can you pick a random edge I such that the probability that that random edge is equal to the ith one is actually Pi? Okay, this is an important building block. If you think about this, it's not that hard to come up with a construction. I'm going to just spoil the construction because I think I don't have time. So here's the construction. Pick one of the edges uniformly at random, flip the corresponding coin. If it was tails, continue. If it was heads, pick the coin and iterate. So as you will see, the way that I'm picking one of the edges is proportional to its probability. At the end, I'm coming up with a distribution over the edges. So that means the probability to pick edge is going to be exactly equal to Pi.
But then you have to repeat this thing. No?
Yes, yes.
You get over 0.
Yeah, good. And so what is the expected run time? So it's like a geometric random variable with parameter equal to summation Pi divided by m, right? At each time the success happens equal to summation Pi divided by m. M is the number of coins. And the expected of this thing is m over summation Pi.
But they add up to 1, yeah?
They add up to 1. This is for the case that you want to like pick the ith one, the probability proportional to Pi, and then you get the summation, otherwise it's going to be just m. Yeah, this construction, if you run it when they are not in the simplex, you come up with this distribution. That the probability that you pick the ith one is proportional to Pi, which is basically Pi divided by summation. Okay, I call this Bernoulli race. Let me show you another problem. I call it exponential Bernoulli race. And you will be soon seeing why this is very important. So exponential Bernoulli race is the following. You want to pick the coin I with a probability that is proportional to e to the Pi. Okay, this is clear. Now, why exponential Bernoulli race matters? Let's go back to our mechanism design question. Recap. We were looking for two things. First of all, we need to allocate one of the surrogates to the agent such that my allocation is near optimal. And second, I need the allocation to be a regularized welfare maximizer. Because there was this theorem that said if you have regularized welfare maximizer, there is a way of making it truthful through some payment. Okay? And suppose you know how to solve the exponential Bernoulli race problem. How can you relate these two together? Here's the way that you can do it. Just think about the entropy regularized welfare. You have the welfare objective, and you add delta times the entropy of the distribution Q. Now, very interestingly, if you solve this convex optimization, then the solution is the following. The QIs are going to be proportional to e to the power vi divided by delta. This is a very well-known phenomenon, like people who are familiar with follow the regularized leader in learning. This is basically the follow the regularized leader. Follow the leader is when you don't have this thing. Follow the regularized leader is when you have entropy. And we know that follow the regularized leader with entropy as a regularizer is basically multiplicative weight update. And this is the distribution of the multiplicative weight update. So these connections exist everywhere. So now here is what I'm doing. I let the delta to be smaller than, let's say, epsilon divided by log m. Then this is going to be bounded by epsilon. So I'm pretty sure whatever distribution this pops out is going to be near optimal, meaning that I'm not going to lose more than epsilon. And now I'm going to show you how, with the help of the Bernoulli race, I'm actually going to do the exponential Bernoulli race, which is exactly the distribution that we need here.
So what is support of Q prime here?
Any number between 0 and 1, such that, I mean, the Q's are in the simplex.
Okay, then Q prime. Then I didn't get your comment about delta being epsilon over log m.
Oh, so it doesn't matter what delta you pick, right? Whichever delta you pick, your distribution is going to be, for I, is going to be e to the power vi divided by delta, divided by summation of e to the vj divided by delta. Okay? Now, so you have the choice for delta. Remember, the objective here is not important, because this is maximizing this objective. What's important is the welfare you get. So if the contribution of this part is upper bounded by epsilon, then the maximizer of this optimization problem is going to be within epsilon range of the maximizer of the welfare objective function. And I know entropy is bounded by log m for uniform distribution.
Bounded by 1, that's why.
What is bounded by?
You're saying Q prime is supported on, it's either 0 or 1?
Oh, no. So this is entropy of a vector.
Oh, okay.
It's not a binary entropy. It's an entropy for a distribution over m points.
Okay, sure.
Yeah, that's a good point. It's not like a summation of h binary of QIs. That's going to be bounded by m, right? Because each entropy is bounded by is between 0 and 1 for uniform.
It's just one choice among all of
them.
So it's
yes, that's my ground set, and I have a distribution bold Q. This is bold Q prime. Mm-hmm. I tried to make it bold to avoid that, but yeah. And that entropy is bounded by log, right? Good. So how to do the exponential Bernoulli race? We know how to do the Bernoulli race. Now think, like, what else can we do? Now suppose somehow from each coin, I can make an exponential coin. So my coin has bias vi. I can kind of do a Bernoulli factory to e to the power vi. Then if I run the Bernoulli race across these, it's going to be the exponential Bernoulli race. And this is essentially what I'm doing. So I have my coins, v1 through vn. So for each coin, I do the exponential Bernoulli factory for the function e to the power p minus 1 divided by delta. And you will see why this function is interesting. And then you do the Bernoulli race across these exponential coins.
So why can you do the middle part? You say that f should be polynomial and things like this. You want to do the Taylor expansion.
There was others. What was the probability generating function, right?
Okay.
I'm going to show you this is a probability generating function. Do you guys know what distribution has this probability generating function? E to the power p minus 1. It's like Poisson distribution. So Poisson distribution has probability generating function e to the power p minus 1. And this is essentially what I mean. Okay, so good. Everything is spoiled. this is the positioning function of a Poisson with parameter polynomial delta. So all you need to do for this Bernoulli factory is the following. You draw x from Poisson with parameter polynomial delta. You flip your coin x number of times. If all the coin flips were heads, announce the heads or announce the tail. And this is going to be this exponential Bernoulli factory. From each coin, you create an exponential coin, and then you run the Bernoulli.
So there is a paper by Yuval Perez and others who say exactly for P, which functions, if you give me this, like what functions are possible to do it, right?
Awesome, yes, that's the most important Bernoulli factory paper. So they show everything is boiling down to implementing function 2P in that paper. So if you can do 2P, then you are in good shape. So you are right that if my function is just like I think the Yuval function is called a Yuval function, which is basically kind of like a continuous, first order continuous function. When P is in the range 0 to 1 minus delta, then you could do this in polynomial time. But my function is so beautiful. I mean, I don't need to even read Yuval's paper. I just need to look at the positioning function of Poisson, right?
Yeah.
So, yeah, but you're right.
This can be done in polynomial.
This can be done in polynomial no matter what this function is kind of. This is, I think, Baldwin's point, right?
Yeah.
Yeah.
No matter what, you can do it even in polynomial
Yeah,
time in P. I mean, if it's 2 to the 2 to the P or something, why can't you do it? I work with weird functions. I didn't get that point. Are you saying complexity-wise also I can always do this in polynomial?
No. I was just referring to, because he said this function, I was referring to his work on like what functions are possible, what is not possible. And
yeah. So
I don't know about the complexity implications.
For you, let's chat offline. Okay. But you can do 2 to the 2 to the 2 to the P. It doesn't matter as long as the function has a sequence of Bernstein polynomials that converge into the function. Okay. Because the Bernstein polynomials, you can do it by just, I'm going to explain. But that's a good point. It doesn't matter how big your function is. First of all, 2 to the 2 to the P is not a probability, right? You should give me a function that maps 0, 1 to 0, 1, and it's continuous, and I can do that function. Good. Okay, so, but this is not polynomial time. Maybe you have noticed why. But if you think about the running time of the Bernoulli race, so what I said was the running time is the expected of a geometric random variable. Now these are exponential, so this can be quite big. Basically, if you count the number of samples, for this guy, the expected value of the Poisson is 1 over delta, which is affordable. But then the number of samples you take in the Bernoulli race is m over the summation of the probabilities that they have, which are e to the power vj minus 1 divided by delta. And now, if all of these values, actually not all of them, if the maximum of them is far from 1 by a constant, then this is going to be exponentially big. So the bad case happens when all of these values are small. If all of these values are small, this can be exponentially big. Now the question is, suppose all of the values are small. What can you do? So we do some pre-processing. This is coming from an interesting property of the exponential distribution. So if you look at the exponential distribution, which is e to the power vi divided by delta normalized, then there is a nice property. If you shift all of the values by some L, then the distribution remains the same. Okay, but I'm not allowed to have a coin and shift its bias. You can't do such a thing. But you can mix it with some other coin that the L has been chosen in a smart way that kind of pushes all the values such that there exists at least one of them close to 1, and then do the exponential. And this is essentially what we are doing. So we create a coin that has bias L, and L is a random variable whose expectation is such that plus max Vj is greater than 1 minus delta. So you can think of L as a random variable that is filling the gap that you have. And now you mix these coins with the help of the multivariate Bernoulli factory that we have for the summation, and then you can do the entire reduction. So if you put all the pieces together, then you get a fast exponential Bernoulli race that has a running time, which is polynomial in m number of the surrogates and 1 over epsilon. Okay.
What was max of Vj? How did you compute that?
Oh, you can sample this time. it doesn't matter. Right? You can take sample from these guys, and then look at the empirical mean, and create a random variable that is high probability in the range that you want, and then use that to fill the gap. Because no matter what L is, the distribution you have over the circuit is exactly the same, and that is exactly an affine maximizer, and that is exactly implementable truthful.
So, Rad, one question. The first thing, why it's a Bernoulli? It's the.
Oh yeah. Okay. Yeah. So. Think about Renato, think about the original problem, right? So these guys are random variables that are values. They're numbers between 0 and 1.
Right.
Maybe I should have said at some point that I assume that the values are between 0 and 1.
I assume you get a value and you round to 0 and is that value.
Yeah, yes. So they're not coins. They're just like some numbers, their expectation are these numbers you want to bring in.
You're saying you sample the value and then you sample Bernoulli's at expectation. And then just that combine.
So what the first part is doing is basically creating a Bernoulli with the same bias from a random variable that is continuous. So you have a random variable which is between 0 and 1, and from that you want to create a coin, which is a discrete thing, right? That the bias is equal to VI. That's easy. Just draw a uniform random variable between 0 and 1 and compare it with your realization. If the realization was smaller than the uniform one, announce a tail, announce a heads, or announce a tail.
No, I think I'm happy, actually. That's good. Thanks.
Yeah, this is basically the first part, but you're right. I tried to trick you guys by assuming that I have access to coins, but yes. So for the original Blackbox reduction problem, we don't have access to coins. We have access to values, the random variables you can sample from. And they're between 0 and 1. You have to create coins from them with the same expectation. And it's easy by just comparing to a uniform between the
That's for me. That's between 0 and 1. Is that?
Yeah. That's actually a very important assumption because the problem scales, right? We have additive. So when you're shooting for additive bounds, then you have to normalize the values. Otherwise, it doesn't make sense.
All right.
If you twice the values, the gap cannot remain.
The ratios in the paper are all additive.
Yes. And I would be interested if someone can get a multiplicative bound, honestly, for the general problem. I don't think it is possible, but we don't have a lower bound.
So if the values are not between 0 and 1, you will lose epsilon times the maximum value or something.
Yeah. So if you can make the epsilon such that it basically scales with the value of the algorithm, then you get a multiplicative bound.
Sure.
But none of the constructions that we have allow such a thing. Because epsilon should be constant at the beginning, otherwise you're going to break the truthfulness somewhere.
But you can have a bound on the optimal from the beginning. And
that is essentially normalized. Yeah. Okay, so we solved the single agent multiple circuit problem, but if you remember, there were like two big issues. The first one was distribution preservation. And the second one was the fact that, okay, you are assigned to the best surrogate. What's the guarantee that the best surrogate gets something in expectation in terms of welfare as the original type? And so this is what I call the welfare preservation, and the other one is type distribution preservation. Okay, this is like almost the last slide. And then here is the way we do it. We are generalizing the max. So the surrogate mechanism design problem was assigning the best surrogate, basically implementing the max function through sampling. Now we are generalizing things to a matching problem. So you want to find suppose you want to find maximum matching by the same machine. Let me go through this quickly. And I think this is the right way of presenting this because for understanding you have to read the paper. But here is roughly speaking what we are doing. So previously we just had the agent and the IID surrogates. Now imagine you have IID draws from the type on one side, I call them replicas, and I have surrogates on the other side. And the object that I'm looking for right now is a matching between the types to surrogates. And actually we are looking at K to 1 matching. K is some parameter in the reduction. Capacity of the surrogates on the right side. And then we find some matching, and then we see who this guy gets matched to, and we announce that surrogate. This is the general reduction. And now, here is a theorem that we are using that actually, if you can, find the maximum matching when, for edges, you have expected values. For the expected graph, if you can find the maximum matching and allocate the surrogate to the guy that gets matched in the maximum matching, then the welfare loss is preserved. And then there is this other interesting property that I can actually prove very easily, which is that you get distribution preservation too. Just use the principle of deferred decisions. These guys are IID draws. You pick some matching here. Let's say it's a perfect matching. And then this is just among them, right? So you can do the following. You can basically draw all the types here on the left side, draw all the surrogates on the right side, pick some matching, and then say the agent is actually one of these guys uniformly at random. Then the assigned surrogate is going to be one of these guys uniformly at random, no matter what matching you pick here. And because all of them are drawn from the same distribution, then you get distribution preservation. This is like an easy trick. And then for the welfare one, you need to use that problem. But I haven't shown you how to do the maximum matching using sampling. And then this is essentially the same idea. You look at the maximum matching problem, and you add entropy regularizer to the objective function. And then the solution is going to be exponential weight for all the left-hand side vertices when the values are shifted by the optimal Lagrangian duals in this optimization problem. And now you have to kind of use the solution that we had for the single agent multiple surrogate problem to do this optimal matching, or let's say this optimal regularized matching. And the way that we do it is kind of complicated. So is that we look at an online algorithm that look through these vertices on the left-hand side, and we try to learn these duals in interactions with the left-hand side in a truthful way. And then we learn the duals and plug them in the surrogate, shift the values, and that's essentially what's happening. So this is what the final reduction looks like.
So it's like you're doing stochastic online matching?
Yes, because the replicas are AD, so you can do a stochastic online matching. But because of some technical reason, we use techniques that are for the random permutation one.
I see. That's why I put this K, because you're in this bit to budget ratio. That's
yes, exactly. So because here, your online algorithm should get 1 minus epsilon approximation. Otherwise, you're going to lose constant amount of welfare. Good. Yeah. So you got it. So we need 1 minus epsilon approximation. So we have to look at the online budgeted allocation, or basically the K to 1 matching when K is much larger than 1. Otherwise, if you, so here's basically the right way of looking at what we are doing. I told you how to do a maximizer, right? Using the Bernoulli factory. So maximizers are the building blocks of the greedy algorithms. And we know that for the maximum matching, greedy algorithms cannot do better than half, right? But for the maximum K to 1 matching, when the left-hand side, the online side is arriving random, they can do 1 minus epsilon, kind of. If you guide them using the dual parameters. This is essentially the idea that we're doing.
And where do you put the right replica, the real one? Because you have the issue where you want to put a real replica.
So one of the replicas, so we don't know which replica is the true replica, right? So you have to treat all the replicas in a truthful way.
So how do you know what's the, you have one replica, then you have one real guy, then you create a bunch of replicas?
Yeah, I don't need to know who is that guy. I just treat all the replicas in a truthful way. He's going to be one of them.
But for the approximation ratio you might need, right?
For what?
For the approximation ratio you might need to have, to know who is the right one. Right? No.
So you mean for finding a dual variables, right?
At the end of the day, you care about who gets matched to the real one. You don't care about the other ones.
Yeah. So, okay. So I know who is the real one, but the algorithm that is taking care of the matching doesn't know that.
Right. But I'm asking, like, do you put it in a random position, or do you put it in the end? Is that a good?
Yeah. Oh yeah. So. Okay, yeah, of course. Like I'm drawing like replicas for other non-true agents, and I put my agent randomly somewhere.
All right.
So that the entire type profile look like a random draw.
All right. So that's
yes. Yeah. So we run this, incentive compatible online entropy regulators matching for each agent, transform the types to surrogates, and plug them into the allocation algorithm, and that's the reduction.
And just once, yes? You only need to call the... Okay.
You need to call the allocation algorithm for the payment also. You need to call it twice for the payments. So actually, you need to call this guy 3 times. And also, you need to call this guy every time you take a sample. Remember, so what is a sample, right? So it's like value function is fixed, type is fixed, and then you need a distribution of outcomes that comes from taking a sample here. But after having the type to surrogate transformation, okay, so the summary is I showed you how to do reduction. I don't have time to go through that. But there is a future problem I want to explain if I have time. This is like some cool open problems.
Very quickly.
Very quickly. So these are basically a generalization of the Bernoulli race problem. Forget, if you don't like mechanism design, this is the perfect slide for you guys. So what was the Bernoulli race? It is basically you have a ground set of elements. You have access to marginal sampling oracles. And you want to pick a combinatorial object. Here is like a base of the one uniform matroid, such that your random selection matches the marginal constant. If you're familiar with entropy sampling, like entropy sampling is saying like you want to find the maximum entropy distribution that matches the marginal conditions. Here is exactly the same thing. But the difference with the entropy sampling is here you have access to marginal distributions. So we solved the problem for one uniform matroid. Now the question is, can you do the k-uniform matroid? Can you do actually the matching one? So I have constructions that show you can do this for a subset of the simplex that is having a non-zero measure, but not the entire simplex. So the matching one is interesting. So you have a W stochastic matrix, row sum up to 1, column sum up to 1. For each edge, you have access to a sampling oracle. Now you want to pick a matching randomly by using sampling from the edges, so that the probability that hij is in the matching is equal to the number that is written on the edge. Think about the numbers as like expectations.
Are they independent, or you want the matching to become?
So think of each edge as a sampling oracle that you can independently sample from that. So you definitely need to pick your matching in a correlated way.
Yes.
But at the end, the marginals should be equal to the marginal probabilities for edges.
But not for the whole matching.
Yeah. And here it doesn't matter whether your sampling is polynomial or not. Just a way of picking your matching using sampling. That would be interesting. Okay, with that, I conclude my talk. Sorry if I went over time. And thanks.